Since the dawn of time, the motion of planets and other celestial bodies has fascinated humans. Throughout centuries, many scientists have observed the behavior of celestial bodies and have tried to come up with models that fit their carefully obtained data. Around 1500, Copernicus proposed the theory that planets move in circular orbits around the Sun. Copernicus used his heliocentric model to estimate the periods and radii of planets. We can determine the velocity and period of a planet in orbit by using Newton's inverse square laws. The gravitational force on a planet of mass mp moving around the Sun of mass ms in a circular orbit of radius r is equal to the gravitational constant capital G times the product of ms and mp divided by r squared. The centripetal force that keeps the planets moving in a circular orbit is equal to the mass of the planet mp times the square of the velocity of the planet divided by the distance r between the planet and the Sun. If we assume a planet moves in a circular orbit around the Sun, we can set the gravitational force of the Sun equal to the centripetal force needed to keep it moving in a circle. Simplifying, we obtain that the velocity of the planet is equal to the square root of the gravitational constant times the mass of the Sun divided by the radius of the orbit. Notice that the speed of the planet is independent of the mass of the planet. Let's do an example. How fast is the Earth moving around the Sun? The mass of the Sun is 1.991 times 10 to the 13th kilograms. The average Earth-Sun distance is 1.496 times 10 to the 11th meters, and the gravitational constant is equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Correct. In much the same way, we can find the centripetal acceleration for a planet in circular orbit. The centripetal acceleration of a planet is independent of the mass of the planet, and it is equal to the product of the gravitational constant and the mass of the Sun, divided by the square of the average distance between the planet and the Sun. Let's compare the centripetal acceleration of the Earth around the Sun to that of Venus. The average Earth-Sun distance is 1.496 times 10 to the 11th meters, and the average Venus-Sun distance is 1.08 times 10 to the 11th meters. Venus's centripetal acceleration around the Sun is A. Nearly twice Earth's, B. About equal to Earth's, C. About half Earth's. Correct. Because the centripetal acceleration of a planet is inversely proportional to the square of the distance between the Sun and the planet, the centripetal acceleration of Venus around the Sun is almost twice Earth's centripetal acceleration around the Sun. We can find the orbital period t of a planet using the expression we derived for the square of the velocity. Recall that the orbital velocity of a planet is equal to 2 pi times the distance of the planet to the Sun r divided by the orbital period t of the planet. By squaring the velocity and setting it equal to the value obtained previously, we can solve for the period t of the planet. Notice that the period of the planet is independent of the mass of the planet. Also notice that the square of the period is equal to a constant, ks times the cube of the average distance of the planet to the Sun. What is Earth's orbital period? Correct. In the 1600s, Johannes Kepler, who was a student of Brahe, used Brahe's measurements and, after 20 years of hard work, came up with 3 empirical laws that governed the motion of planets. Kepler's first law states that the orbits of planets are ellipses, with the Sun at one focus. This law is also called the law of orbits. Kepler's second law states that a line running between any planet and the Sun sweeps out equal areas in equal time intervals. This is also called the law of areas. One conclusion that we can draw from this law is that the planet shown in the figure moves faster between points 1 and 2 than between points 3 and 4. Kepler's third law states that the square of the period of any planet moving in an elliptical orbit around the Sun is proportional to the cube of the semi-major axis of the elliptical orbit. This is also called the law of periods. Since the orbits of all planets except Mars, Mercury, and Pluto are nearly circular, the average distance r from the planet to the Sun is equal to the semi-major axis, or, in other words, A is equal to r. Therefore, the square of the period t of a planet is equal to a constant ks times the cube of the average distance r from the planet to the Sun. Recall the expression we obtained for the period of a planet using Newton's inverse square law and centripetal acceleration. It has the same form as Kepler's third law. Now let's look at the circular motion of a body of mass, small m, around a massive body of mass, capital M. We can use Newton's law of gravity to calculate the potential energy of the system U. Since gravity is a conservative force, the work done by gravity equals the negative of the change in the potential energy associated with the gravitational force. Carrying out the integration and taking the initial potential Ui to be 0 at infinity, we obtain that the final potential energy U of the system is equal to minus the gravitational constant g times the product of the masses divided by the radius r of the orbit. The kinetic energy of the system is equal to the sum of the kinetic energy of the orbiting mass and the kinetic energy of the larger body. However, assuming that the massive body is at rest, in an inertial reference frame v equals 0, the kinetic energy of the system is thus equal to the kinetic energy of the orbiting mass. The total energy E of the two-body system is equal to the sum of the kinetic energy and the potential energy of the system. The force acting on the body of mass, small m, is the gravitational force, which is also the centripetal force. Multiplying both sides by r and dividing by 2, we obtain an expression for the kinetic energy in terms of the gravitational constant g. The kinetic energy is positive, and its magnitude equal to half that of the potential energy. Substituting this into the equation for total energy, we obtain that the total energy of the system is equal to negative g times the product of the two masses divided by twice the radius of the orbit. This shows that the total energy must be negative for a circular orbit. The physical interpretation of this negative mechanical energy is that the body of mass m is bound to the more massive body and can never escape from it. This negative value of E indicates a binding energy. For an elliptical orbit, the total energy has the same form. In this case, the radius r is replaced by a, the length of the semi-major axis. Let's do an example. Calculate the energy that constrains the Earth to orbit around the Sun. Use the expression we found for the total mechanical energy E, with the mass of the Sun, capital M, equal to 1.991 times 10 to the 30th kilograms, the mass small m of the Earth, equal to 5.98 times 10 to the 24th kilograms, and the mean distance between them, 1.496 times 10 to the 11th meters. Use the gravitational constant G, equal to 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. Correct. Now let us suppose an object of mass small m is projected straight up from the Earth, whose mass we this time call capital M. Can we find the speed with which it must be projected to escape the gravitational pull of the Earth? The total mechanical energy of the rocket at any point is given by the energy equation that we used earlier. On the surface of the Earth, r is simply the radius of Earth RE, and let us call the initial velocity of the object on Earth v sub I. In this case, the total mechanical energy is 1/2 mvi squared minus the gravitational constant G times the product of the masses of the Earth and the rocket divided by RE. At the maximum altitude, the velocity of the rocket is 0, and we'll call its distance from the center of the Earth r max. The total energy reduces to negative g times the product of the mass of the Earth and the mass of the rocket, divided by the maximum altitude r max. Since total mechanical energy is conserved, the total energy of the projectile on Earth should equal its total mechanical energy at the maximum altitude. By setting these two values equal and simplifying, the initial speed to escape the gravitational pull from Earth is given by the minimal escape speed is then obtained by setting r max to infinity. This is the speed for which the projectile will reach infinity with a final speed of 0. Therefore, the initial velocity is equal to the square root of 2 times g times the mass of Earth divided by the radius of Earth. We obtain that the initial velocity is equal to the square root of 2g times the mass of the Earth divided by the radius of the Earth. Let's do an example. Calculate the escape velocity of a 3,000 kilogram rocket from the surface of the Earth. The mass of the Earth is equal to 5.98 times 10 to the 24th kilograms, and the radius of the Earth is equal to 6.37 times 10 to the 6th meters. Correct. Notice that the result of 11.2 kilometers per second obtained does not depend on the projectile's mass. Thus, this value is the value of the escape velocity of any object from the surface of the Earth. Now let us look at the motion of a satellite in an elliptical orbit around the Earth, and try to figure out its velocity at any point on its path. In this case, the gravitational force acting on the satellite is a central force, always acting along the radial vector towards the Earth. The torque acting on the satellite due to this force, F, is equal to the cross product of R and F, which is equal to 0 since R and F are parallel to each other. But remember that torque is equal to the derivative of angular momentum with respect to time. If the time rate of change of a quantity is equal to 0, that quantity is constant. So the angular momentum L of the satellite is always constant. Since the angular momentum L is equal to the cross product of the radial vector and the momentum vector, a constant angular momentum means that the motion of the satellite is restricted to the plane formed by r and p, or equivalently by r and velocity v. At the apogee and perigee of the elliptical orbit, the velocity vector v is perpendicular to the radial vector. Therefore, the sine of the angle is equal to 1, and at those locations, the angular momentum is equal to the product of the velocity, radial distance, and mass of the satellite. Setting the values of angular momentum at these 2 points equal to each other, we obtain that the product of the velocity and the radial vector is the same at the perigee and the apogee. This implies that when the satellite is closest to the Earth at the perigee, its velocity is at its maximum, since r is at a minimum there. At the apogee, since the distance is at its maximum, the velocity is at a minimum, and thus the satellite moves fastest at the perigee and slowest at the apogee. Simplifying, we obtain the value for the velocity at the perigee in terms of the velocity at the apogee. So, by setting the angular momentum of the object at a point equal to the angular momentum at the perigee or apogee, and solving for the velocity, we can obtain the velocity of the satellite for any point on the orbit. In much the same way, the previous relations can be applied to a planet moving along an elliptical orbit around the Sun, so its velocity at any point of the orbit can be calculated in terms of its velocity at aphelion or perihelion. Let us do an exercise. The distance between Mercury and the Sun at Mercury's aphelion is 7 times 10 to the 10th meters, with a speed of 3.88 times 10 to the 4th meters per second. If Mercury's perihelion is 4.6 times 10 to the 10th meters, what is the speed of Mercury at the perihelion? Incorrect. Try again. Correct.